This is the 6-5 and 7-7 review, number 7, and calculators are allowed. So if we look at this one, it says for the first month of life, the weight gained in ounces of a newborn 2 weeks after birth is modeled by this equation. Then the question is, what is the average rate of change in the newborn's weight during that third week of growth? So a few things that are built into here that can be a little tricky. The first thing is people see this average and they think they need to do 1 over b minus a times the integral from a to b time of whatever it is we want the average of. So what people mess up on here is they just do the average of w instead of the average rate of change. So if I want the average rate of change, this is another way of saying w prime of t. So that means I will be taking the integral of w prime dt. Now the next place that people mess up is they misinterpret this third week of growth and they get the wrong endpoints. So let's just think about a timeline. When that baby is born, time is 0. So by the time he hits week 1, he has had his first week of growth. So that means if he hits his second week, it's going to end with 2. The third week is going to end with 3. So the boundaries for that third week of growth are actually 2 to 3. So that means my a and b are going to be 1 over 3 minus 2 times the integral from 2 to 3. Now, because I want to find the average rate of change, I have to answer the question, what did I take the derivative of with respect to time that gave me w prime? And the answer to that is w. So I'm going to plug 3 into w and 2 into w, and I'm dividing by time, so I'll end up with that ounces per week. Now I'm going to trust that you can put that into your calculator and evaluate it with 3 and 2 and subtract those. I won't waste time on the video doing that because you'll end up with 0.455 ounces per week. So now let's look at B. B says the depth of water is represented by this formula, and I want the average rate of change in the depth. So again, I'm doing that average rate of change, which means I'll have 1 over the b minus a integral from a to b of the rate of change. And I want to go from 3 to 5, and t is time starting at midnight, so that one's going to be a 5 minus 3. Nothing tricky on those time intervals like on part A. So if I finish this, it'll be a 1 over 2 times what did I take the derivative of with respect to time that gave me h prime? Well, that's h evaluated from 3 to 5. So we'll end up with h of 5 minus h of 3 over 2. Now just a quick little aside, if you remember way back at the beginning, back in chapter 2, we talked about average rates of change and we talked about instantaneous rates of change. And if you remember, average rate of change was a secant slope on the original function. And notice that I have a y minus a y over that x minus the x. So this is our secant slope, and we had the same thing up on the original on part A. So I'm going to assume you can plug h into your calculator and then evaluate at 3, evaluate at 5, do your subtraction, and you'll end up with 0.224 feet per hour. Okay, last part C. This one says the temperature of a metal rod that is 6 meters long is 5x in degrees centimeters at a distance x meters from one end of the rod. What's the average temperature? So I gave you the temperature at any time was 5x, and I want the average temperature, so that will be 1 over the integral of that temperature, because that's what I want the average of. So let's think about what the limits are. It's 6 meters long and I want the entire rod, so that would be from 6 all the way down to 0. So now I've got to answer the question. What did I take the derivative of with respect to x that gave me 5x? And the answer to that is 5x squared over 2, and I evaluate from 0 to 6. Plug in the 6, I have a 5 times a 6 squared over a 6 times a 2, and then I'll subtract 0. So I could use my calculator, or I can just simplify. 6 will go in, and then I'll have a 3, so it looks like I end up with 15 degrees centigrade.